Let's continue from where we left off in our last lecture and discuss more concepts related to probability. In the last lecture, we defined variance and covariance and proved a couple of definitions that make them easier to compute. We'll now look at properties of the variance. So given two random variables, x and y, and constants, a and b, that lie in the real line, if you recall, the real line is just the whole line of numbers from negative infinity all the way up to infinity. 0 lying right in the middle. Any number, any decimal, integer, whatever it may be that takes the value from negative infinity to infinity. So this a and b, these are just constants, any type of constant, i.e. they're not random. So given a random variable x, what is the variance of a times x plus b? Well, it turns out that you can eliminate the b, and the constant a gets pulled out of the variance as in the expectation, but this time it's squared. So you get a squared times the variance of x. The variance of the sum of two random variables, that's a little bit more complicated. Well, so you do pull out the scaling constants, the a and the b, they come out of the variance, and they come out squared as before. And the variance operator, it goes through the summation so that you have the sum of one variance. Well, the variance of the sum ends up being the sum of the variances, but then you get this extra term that makes the sum of the variances not equal to the variance of the sum right here. And this extra term is the covariance between x and y that you need to account for. And the way you scale that is you pull out the a and the b, and you also pull out a 2 to account for the covariance of x and y and the covariance of y and x, which is symmetric, and they turn out to be the same. We'll prove this in the next slide. So this latter property, it can be generalized to many random variables. So for example, let's say you have n random variables, and we're going to call them all some form of x, and we're going to index them by xi. So that what you have is one random variable called x1, another one called x2, another one called x3, and these are very different random variables, and so on, all the way up to xn. And each one of them has associated with it a constant that scales it, a3, an. Well, just as before, the constants will come out of the variance, so they come out. Well, first of all, the variance is going to go through the summation, so that you get the sum of the variances, and all the constants will come out of the variances squared. And then you get the cross products, which are all the covariances scaled by each of the scaling constants and a 2. So what are we doing here? It turns out that this double summation is just actually adding all the pairwise covariances. That's all it's doing. So it's taking x1 and then it's matching, it's including the covariance of x1 with x2, 3, 4, and 5, and it's adding all those together. And then it takes x2 and it does not take the covariance with x1 because we've accounted for that with the 2 already. And it just matches the covariance of x2 with x3, x3 with x4, and so on, all the way up to xn. So let me be a little bit more explicit with these covariance cross products. So let's say that we have 4 random variables, x1, x2, x3, and x4. Let's leave off the constants for a moment. So the variance of x1 plus x2 plus x3 plus x4 is going to be equal to the variance of x1 plus the variance of x2 plus the variance of x3 plus the variance of x4 plus, and then I need to add the covariance of each with the other. So if I don't I'm not going to multiply by any 2's. I'm just going to literally take each covariance. So cov x1, x2 plus cov x1, x3 plus cov x1, x4. Now I'm going to add in, I'm going to do the, starting with x2, cov x2, x1 plus cov x2, x3 plus cov x2, x4 plus cov x3, x1 plus cov x3, x2 plus cov x3, x4 plus cov x4, x1 plus cov x4, x2 plus cov x4, x3. Interestingly enough, all these variance terms that I started with, I didn't really need to do them. What I could have done is cov x1, x1 plus cov x1, x2 plus cov x1, x3 plus cov x1, x4. But the cov x1, x1 would have been variance x1. And then I could have started with the 2's and done x2 with x1, x2 with x2, which ends up being that term, x2 with x3. So really all I'm doing is I'm summing all the pairwise covariances, and it turns out that these variance terms are just the covariance terms of each one with itself. Now we also notice that covariance is symmetric. The covariance of x1 and x2 right here is the same as the covariance of x2 with x1. So this is where the 2 comes in. I eliminate this one and I put a 2 in front of that one. Likewise, I can find covariance of x1 with x3. That's the same as covariance of x3 with x1. So let's eliminate that one and let's put a 2 in front of that one. Now let's find covariance of x1 with x4, x4 with x1. Let's eliminate that one, put a 2 there. We can eliminate this one, x3 with x2, and put a 2 in front of the x2 with x3. We can eliminate the x4 with x2, and we put a 2 in front of the x2 with x4. And then finally, we can eliminate this one and put a 2 here. So instead of doing all the pairwise covariances, what we do is we simply start with x1. We take the covariance with x2, x3, and x4, and we multiply them all by 2, and then we don't go backwards when we compute the pairwise. Starting with x2, we just go forwards, x2 with x3 and x4, multiplying those by 2. And then when we start with x3, we don't consider those because we've already added them in by multiplying by 2. And so then we just add in the x3 and x4. Double sum, that's why the double sum ends up looking like this. It ends up being the summation of I starting at 1 going up to j. Look at that. It's not going up to n. And then j starts at 1 and it goes up to n. And then we're doing cov x I with xj. And we're doing 2 of every one of those. This is the same as saying I equals 1 to n, j equals 1 to n, cov xi xj. Because what this is doing is it's saying start with I equal to 1 right here. And then with I equal 1, let's actually take the covariance of x1 with each of the other x's, j all the way up, from 1 all the way up to n. So you're taking the covariance of x1 with each of the others. Then you increment I up to 2, and then you do the same thing. You take x2 covariance with each of the others, j equals 1 up to n, which adds in all the other terms, including that one variance term, including j equals 2, which would be cov x2 x2, which is a variance of x2. So in reality, we don't need to take I from 1 to n, we just have to take I up to j and then add in 2 of everything else and let j go from 1 to n. An alternative way to visualize this is to say if we have random variables x1, x2, x3, and x4, we can formulate them as a matrix. We can put, I'm going to call the covariance term sigma 1, 1, that's actually the variance. That's the covariance of x1 with itself. That's what that notation means. I'm going to use sigma as covariance now instead of variance. And then the 1 and the 1 means x1 with x1. So that's actually a variance. I'm going to do covariance of 1 with 2, which is sigma 1, 2, sigma 1, 3, sigma 1, 4, sigma 2, 1, sigma 3, 1, sigma 4, 1, sigma 2, 2, sigma 2, 3, sigma 2, 4, sigma 3, 2, sigma 3, 3, sigma 3, 4, sigma 4, 2, sigma 4, 3, sigma 4, 4. Okay, so the sigmas are simply all of the covariance terms. On the diagonal of this matrix, what do we notice? These are the covariance terms of each random variable with itself. So it turns out the diagonal of this matrix is very special. It contains the variance terms. So what we really want to do when we compute the variance of x1 plus x2 plus x3 plus x4 is we just really want to add together all of the terms in this matrix, which include the variance terms. Now what we do when we do the double sum and multiply by 2's, we're adding the variance terms, and then we're just adding 2 times these terms, and we're not adding any of these terms below the diagonal. Why? Because it turns out that this term is equal to that term is equal to that term is equal to that with that with that with that. And so instead of adding in all of these terms, we can eliminate them and just multiply each of these by 2, and then we add in the diagonal terms and 2 times all the off-diagonal terms, the upper part of the matrix or the lower part of the matrix, and we'll get to the same number as we would have if we just added all the terms together. So that's all that double sum is doing. The double sum is simply counting in all of the upper part of that matrix with the variance terms. Alright, now it's time for a proof. So the first property, we have variance of AX plus B. Well, by definition, what is that? It is the expectation of AX plus B minus the expectation of AX plus B, so that deviation squared. Well, we first need to do an aside. We need to figure out what is the expectation of AX plus B. Well, we know from the properties of expectation that that's just equal to A expectation of X plus b, which I'm going to call a mu sub x plus b, just so that we don't have all these expectations flying around. Now let's continue from this point. What is this equal to? Well, substituting in, we get expectation of a x plus b, all this minus a mu x plus b. We're going to take that deviation squared, and it's the expectation of that whole thing. Carrying the minus sign through, we see that this is expectation of, well, b minus b is going to cancel, and the a's are going to factor out, so that we're going to have a x minus a mu x. I'll factor in a second. Remember, that's squared. Now we see where the a squared comes in. So that we're going to pull the a squared out right here. It's going to become squared, and then we can pull it out of the expectation again because it's just a constant. So that we end up getting a expectation of x minus mu x squared. Now what is this quantity right here? That's the variance of x by definition. So what we, sorry, I should have squared the a back here. So what we have is a squared expectation, sorry, a squared by definition variance of x. So what happened? Since b is a constant, it doesn't vary at all. So when we add in the variance of b, we could likewise use that definition more generally, plus the variance of b. Well, that's 0 plus 2 times the covariance of x and b. Well, b is not varying, so this also is 0. It doesn't covary at all with x if it's always the same value and x is moving around. So these two terms don't pop up, and only the terms with random variables pop up, and hence a squared plus x. Sorry, I meant to say a squared variance of x. Now to prove the next property with just 2 random variables, it's going to be very similar. Variance of a x plus b y. By definition, that's equal to expectation of ax plus by quantity minus the expected value of that quantity. And then we have to square the deviation and take the expectation of it. Well, what exactly is that quantity? Here's our aside. We know from the properties of expectations that this expectation is equal to a expected value of x plus b expected value of y, which I'm now going to call a mu x plus b mu y. Okay, now continuing from where we left off, this is equal to expectation of ax plus by, that quantity, minus a mu x plus b mu y. That whole deviation needs to be squared, and we take the expectation of it. And now let's group things. This is equal to expectation of ax minus a mu x plus b y minus b mu y. That whole quantity needs to be squared. So let's group again one more time. let's pull out, that is factor out the constants. So we get expectation of a squared well, I'm sorry, we can't factor out the constants yet. We can only factor them out of the first terms, not out of the squared. So we get this plus this. That whole quantity gets squared, and we're taking the expectation of that. Okay, now we need to expand. This is our first term, this is our second term, so we know when we have two things being squared, a sum of two things being squared, we can expand, so that is equal to expected value of the first thing squared, which is a squared x minus mu x squared, plus the cross product of this thing with that thing, which is a b x minus mu x y minus mu y. Then we have to take the cross product of that thing with that thing, but because of symmetry, that's the same as the first product we just computed, so we just throw a 2 in front of that, and then to finish it off, we just take the final term squared, which is plus by minus mu y. B squared minus that deviation squared. Wow, that's a big term, right? But now we know exactly what to do. We know that the expectation can go through the summation. We know that this constant will come out. We know that this constant will come out. We know that this constant will come out. We know that this will be a squared times the expectation of this quantity, which happens to be the variance of x. We know that this will be 2ab times the expectation of this quantity, which is the covariance. And we know that this will be b squared times the expectation of that quantity, which is the variance. So if we continue, this is equal to a squared expected value of x minus mu x squared plus 2ab expected value of x minus mu x y minus mu y plus b squared expected value of y minus mu y squared. And like I said, this is variance of x, this is variance of y, this is the covariance of x and y. So this is equal to a squared var x plus, and I'm going to add in the last term first just to keep the sequence as the same as in the previous slide, plus 2ab cov xy. Now you see where that 2 came from, right? First of all, you see where the squareds came from. The squared terms come from the fact that when you take the definition of variance has a squared in it, and anytime you factor out a constant, it's going to end up pulling up the squared. The second part is, you notice the 2 comes from expanding the definition of variance and the cross product terms being symmetric. So now that we've discussed the properties of variance, let's discuss the properties of covariance. So given some random variables w, x, y, and z, and constants a and b, it turns out that the covariance of any random variable with a constant is 0. That's because covariance is measuring how variables vary together. A constant never varies, and so it can't vary with anything else. So the covariance of a constant with anything is always 0. Then, this should be apparent from our previous proof, the covariance of A, X with B and Y is just AB times the covariance of X and Y. That should be very easy to show now using the definition of covariance. And then this one's a little bit more interesting. The covariance of the sum of two random variables with the sum of two other random variables, well, that is just all of the pairwise covariances. This should not be shocking given what we just saw from the previous variance of a sum, how the variance of a sum ends up picking up all the cross product terms. Well, the covariance is just a generalization of the variance, and so it picks up all the cross product terms. In fact, you can recall how I noted this in the previous slide, how variance of a sum, let's say x1, or let's call it x plus y, is equal to the covariance of x plus y with itself, x plus y. And how did we get that? Well, that turned out to be the covariance of all the cross product of all the product terms, including x with itself, which is the variance, cov x y plus cov y x. Turns out these two are the same, right? Plus cov y y, running out of space there. And the cov y y is the variance. So the latter two properties of covariance can be generalized to this. If we have n random variables right here, and we label them as x's with the i's, and if we have m other random variables indexed by j, and these we are calling y1 all the way up to ym, all scaled by these constants a1 all the way up to an, and b1 all the way up to bm, well, it turns out that we're just going to sum all of the potential cross product terms multiplied by those constants. So the covariance of two sums is just the sum of all of the potential covariances between those two sets of random variables. I think that this latter property should be fairly easy to prove now. I'll just set up the first few steps, and I think the rest will become apparent given all the work that we've done in the past few slides. So if we say the cov of this sum I equals 1 all the way up to n, so we have these n random variables that are the x's, and then we have these m random variables that are the y's. Well, by the definition of covariance, that is equal to the expectation of the sum I equals 1 to n minus its expectation. The sum of the ai's and the xi's, and that quantity times this new random variable, which is the sum of random variables, minus the expected value of the sum bj, yj, right there. Sorry, we don't need that parenthesis there. And it's the expectation of that whole product. So really what we're doing is we're just relabeling this as some random variable, whatever you want to call it. This could be a random variable Eric, and this could be a random variable Jimmy. And so what we're really doing is just saying cov of Eric with Jimmy is equal to the expected value of Eric minus the expected value of Eric, sorry. Let me rewrite this. Equals cov of Eric. Sorry, expected value of Eric minus the expected value of Eric, right? Times Jimmy minus the expected value of Jimmy. And then we take, so that's why it should not bother you that I'm taking this whole thing and I'm taking the expectation of that whole thing. Don't get confused, I'm taking that random variable right there, which happens to be a sum of random variables, but it's this quantity minus its expectation right here. So Eric minus his expectation, and then Jimmy minus his expectation right here. Well, if we follow through with the math, we begin by saying, well, we know by the properties of expectation that I can take the expectation through so that this expectation of the sum is just AI, well, it's the sum of AI times these expectations. And then this expectation likewise goes through so that we have something that looks like this. Minus, and now I'm taking the expectation through each of those terms, the sum of the AIs times the expectations. And I'm going to do that likewise for the second term. I have these BJ's, YJ's minus the sum of the BJ's times the expectation of the YJ's. And I'm taking the expectation of that whole thing. Well, what we notice is that we can group these terms under the expectations. We can actually pull the summation through since it's indexed by the same thing, right? And this is j equals 1 to m. This is a j equals 1 to m. So we can group all these things and pull out the constants and say this happens to be the expectation of one sum AI times xi minus the expected value of xi. And don't forget, those things all need to stay together. And then we have this sum of the bj's, and then we have the yj minus expected value of yj. And now you're beginning to see that I have what looks like this term with this term are going to result in a lot of cross products because of these summations. And those are going to be all of the covariance terms. So what I'm going to do is I'm going to end up taking the expectation. I'm going to end up first, before I take the expectation through, I'm going to multiply all the cross products between these two sides, which is going to result in a double sum. Okay? So before I take the expectation through, I'm going to result in this double sum of I equals 1 to n, j equals 1 to m of the AI bj, and then these deviations xi yj minus expectation of yj. And now you see as I take the expectation through, I'll have all these covariance terms. And that should set you up to finish off the proof. Now the correlation, this is a special object that's very similar to covariance. It's essentially just the covariance scaled by standard deviations. it's not too hard to show that the covariance must lie between, the correlation must lie between -1 and 1. The properties of correlations of sums of random variables, they follow from the covariance and standard deviations above. So you can actually prove this property right here just using the same tricks that we've been using in the previous slides. And you can also show that the correlation of sums of x with sum of x and y, or x1, x2, x3, x4, with x, y1, y2, y3, and y4, that those will have the same types of properties where you'll just get the double sum of all the scaling constants and so on. Actually, the scaling constants will pull out, but you'll just get the double sum of all the correlations. Now, the normal distribution, this is a very important distribution in all of probability and statistics, and it is likewise very important for much of what we'll do in investments, because it simplifies things, it's tractable, it makes things easy to conceptualize and to compute. So the normal distribution is a continuous distribution, it's not discrete, so that means a normal random variable can take any number in the real line, anything between -infinity and +infinity. The normal distribution is also symmetric, so it has as much mass below its mean as it has above the mean, and the balance point would be right in the middle at the mean. Finally, what's really convenient about the normal distribution is that it's fully characterized by two parameters, the mean and the standard deviation, or the variance, whichever one you want to deal with. So what does that mean that it's fully characterized? It means if you tell me that I am dealing with a normal distribution and you give me the mean and the standard deviation, I can plot every point on the distribution. I don't need any more information than that. And so that is enough, that information suffices, or those parameters are sufficient to parameterize the whole distribution. So here are some examples from Wikipedia. I pulled this graph from Wikipedia, some examples of normal distributions. Everything but the green density, these are, well, we can call these density functions. Everything but the green density is centered at 0. We show that the green actually has a mean of -2, and then these normal distributions have varying variances. You can see over here the sigma squared parameters show varying amounts of dispersion. The blue is the least dispersed right here. It's a very tight distribution. The red is more dispersed than the blue, which is why it has a larger variance. It has a variance of 1, whereas the blue only has a variance of 0.2. This yellow or gold, whatever you call it, it has an even larger variance, which is why it's more spread out than the blue or the red. And then the green, it has a variance of 0.5, which is somewhere in between the blue and the red, but it also is shifted. It has a locational shift, and it has a mean here of -2, which is why the center is found right there. So some nice examples of normal distributions. Now in notation, we will say x is a normal random variable, and we will use this tilde to say that it's distributed as, and then the n says a normal, with the parameters mu and sigma, which, as I mentioned on the previous slide, fully define that normal distribution, mu being the mean, sigma being the standard deviation. So if you see the notation n, and then in parentheses 2 parameters, that means a normal distribution with mean in the first position and standard deviation in the second position. So x is distributed as a normal random variable with mean mu, standard deviation sigma. It turns out that when x is distributed as some general normal with those parameters, that we can define a new random variable using this transformation right here. We just say z is a random variable, where what we're going to do is subtract the mean from x and divide by the standard deviation. It turns out that random variable is very special. It's called the standard normal. Standard because it's been standardized. It's had its location moved back to 0, and its variance has been standardized to 1, so that it has a 0 mean and a unit standard deviation, which is exactly what this says. We can prove this by saying, well, actually I'm getting ahead of myself. I'm going to prove that on the next slide. But let me say this. We can reverse the process by first saying, what is a normal random variable? Begin with a standard normal random variable right here that has unit standard deviation and 0 mean. And then using algebra right here, we can just define z times sigma plus mu as x. So it starts out with something that has unit standard deviation. It expands, it gives it whatever standard deviation here that you're multiplying by, and then it adds a mu to every value that you could possibly have here, which actually shifts the mean from 0 all the way up to mu and gives you a random variable that's normal with that mean and that standard deviation. So this is a way that you can construct a general normal random variable with that mean and that standard deviation. You begin using some software to generate a standard normal, then you multiply by whatever standard deviation you want it to have and add whatever mean you want it to have, and that the resulting value, so if you draw 1,000 of these things, these z's, and multiply them all by that and add to them that, then you will have 1,000 random variables that are from this distribution instead. Okay, now the proof. So the expected value of z, that is equal to the expected value of x minus mu over sigma. And from the properties of expectations, we know that sigma and mu are just constants. They are the fixed mean and standard deviation. So what we do is we pull out the sigma. We say that's the expected value of x minus mu. And continuing, we say that is, we can distribute the expectation through that sum. We call it a sum even though it has a negative value here. It's just a sum of x plus negative mu. So we say that's expected value of x plus the negative expected value of mu. What do we know? We know that the expected value of a constant is just itself, which is mu. We also know that the expected value of x is mu. So what we have here is mu minus mu, which is 0. Sigma times 0 must be 0. So this highlights a very nice property that you should memorize. The expected value of any random variable minus its mean must be 0. You are by definition subtracting its mean from every possible realization of that expected value. So taking the expectation and then through and then subtracting off the mean, you're always going to end up with a mean 0 random variable. Now let's compute the variance of this. So the variance of z, well, that's equal to variance of x minus mu all over sigma. Using our properties of variance and knowing that sigma is just a constant, we know that we must square all constants as we pull them out. In reality, what I'm doing is I'm squaring the whole 1 over sigma, which is equal to 1 squared over sigma squared, and so I don't need to have this squared here. I just put it in the denominator. And now I still have inside variance of x minus mu. Well, we know that the variance of the sum of a random variable and a constant is actually just the variance of the random variable. The constant adds no variance and adds no covariance to that. And so what we end up with is 1 over sigma squared variance of x. What is the variance of x? Well, the standard deviation is sigma, so the variance must be sigma squared. So that's 1 over sigma squared times sigma squared. And guess what? That's a variance of 1. So we've now proven that for any random variable with that mean and that standard deviation, if we transform it and form this new random variable z equals to that original random variable minus its mean all over its standard deviation, that new random variable will have 0 mean and unit standard deviation. Now, another very nice property of normal distributions is that if you take a whole sequence of normals, we'll call them xi's from I equal 1 to n. So we have n normal random variables, each with their own mean and their own standard deviation. Well, if you call w the summation of these random variables, so now I'm going to take all these n random variables that are normals with differing means and standard deviations. So that is, one might be very dispersed and have a mean over here. One might be very sharp and have a mean over here, and another might be somewhere in between. So each random variable has its own mean and standard deviation. If we sum all of these random variables, forming a new random variable that we call w, well, that w is also normally distributed, and its mean is the sum of the means, and its standard deviation, well, we know that we computed. Let's actually disregard this radical sign for a moment. The variance of a sum of random variables should be the sum of the variances plus 2 times all of the cross covariances. So the standard deviation then is just the square root of that. So what we have to do is just say, what is the mean of w? Well, that's the sum of the means. What is the variance of w? Well, that's the sum of the variances plus 2 times the sum of the upper diagonal of that covariance matrix that we had before. And the standard deviation being the square root of that, w is a normally distributed random variable with that mean and that standard deviation. It's a very nice result, and one that will be very handy when we discuss portfolios of multiple assets. So how does this specialize if the covariance of x, of all the x's among themselves are 0? Well, you end up eliminating all of these terms because they're all equal to 0. So this whole thing wipes away, and you end up with just the sum of all the variances under the radical sign. It makes things a little bit simpler to compute. Now let's talk about some sample moments. In reality, we don't, when we're given realizations of random variables, we often don't know what the mean, the true mean, and the true standard deviation are. And so what we need to do is estimate them. So let's say there's some random variable x, and we have no idea what its mean is, but we do have a realization, that is, a set of observations that are realizations of this random variable. We have n observations. Then what we can do is we can estimate the mean with just the simple mean formula. We take all the x's, we sum them, and we divide by 1 over n. This is simply just the arithmetic average, or we can think of it as the probability weighted average, but using probability weights 1 over n. Recall that the true mean, mu, is equal to the sum, if this is a discrete random variable, of all possible values, xi, well, we'll not have xi, of all possible values in that calligraphic set x. So little x times its probability. And what we're doing is we're saying, well, let's suppose that our set is just comprised of our n realizations that we have here. And instead of weighting by some unknown set of probabilities, we're just going to give them equal weights. Well, that may seem a little problematic because the true mean is a weighted average using the actual weights, and that those are not really going to be, or in most cases are not going to be, equal weights. Those probabilities in that probability weighted sum are most likely to be very different from each other. So how do we reconcile the fact that we're using an arithmetic average with equal weights to estimate something that's really a probability weighted average? Well, it turns out that that random sample of n realizations of the random variable, those are not really a fair draw from the whole set of possible values of x. They are actually coming inherently weighted by the true probabilities. So let's say n is a very large number. Then it turns out more values are going to be sampled, that is, more values in the sample will end up being drawn from higher probability regions of the distribution. So weighting them equally just inherently gives them the probability weight of the distribution. Think of it this way. If you have a normal distribution and you just pull a random sample from this distribution, you're more likely to pull values from these high probability regions. And so if you pull 10,000 values, you're going to get this value, that same value or values very close to it many times. But these values you're going to get very few times. And so if you end up with this one value right here, if you end up with that value in your sample 5 times, giving it an equal weight of 1 over n actually weights it 5 over n because you're adding them all together. And so equally weighting is actually the right thing to do because these things are already drawn from the more concentrated region of the distribution. That's what I mean by these samples, these sample values are inherently weighted, and so we don't need to try to incorporate those probability weights when we do the sum. Now we want to compute an estimate of the variance. So in a similar fashion, it looks like there's a typo here actually. This quantity should be squared. So in a similar fashion, we'll just say, let's begin by estimating the mean with just the sample average, the arithmetic average of our sample. Let's take all the deviations from that estimated mean, square them, and then let's just take the average of that, which is essentially the analog of taking the expectation. Well, you see that we're essentially computing a sample average here. I'll tell you about this n minus 1 in a second, but think of it as 1 over n. So that we're just doing a sample average of the squared deviations, which is more or less what you're doing here when you take the variance. The expectation, then, we're substituting a sample average of these types of things, where we have now estimated mu to be mu hat. Now, why are we using the 1 over n minus 1 instead of 1 over n? Well, it turns out that because we had to use a sample average to estimate the true mean, there is going to be additional error in our estimate because of the error inherent in our estimation of that. And if we simply use 1 over n, it underestimates the amount of error in this whole quantity on the right-hand side. And so what we do is we remove 1 degree of freedom, is the terminology. We subtract 1 from the n, and that actually makes this number a little bit larger, which accounts for the error in our estimation right here. So what we've just done is we've shown how to estimate the mean and the variance, or the standard deviation, which would just be the square root of the estimate of the variance. But other types of moments, we call these moments. The mean is the first moment, the variance is the second moment. Correlations and covariances are also types of moments. So other moments of the distribution, like the covariances and the correlations, can all be computed in a similar fashion. I'm not going to actually write them all out here, but all you really have to do is just take the previous definitions from this lecture, and everywhere you see an expectation, just substitute a sample average. So where an expectation is the actual probability weighted sum or integral, now you're just going to take your sample and you're going to do an arithmetic average everywhere there's an expectation. So you're going to do equal weights, because the values underneath the summation of your arithmetic average are already inherently weighted by the probabilities, having been drawn from the more dense regions of the probability distribution.